Okay, so for today's session, we are going to go over the rest of chapter 16, which is the benzene synthesis like techniques and strategies, where we're going to cover polysubstitution, where like there are multiple groups on the benzene ring, like multiple EDGs, multiple EWGs, and how to tell which group directs the electrophile. We're going to go over how to convert in between ortho paradirector and metadirectors. We're going to look at the ortho and para products, which one is major, which one is minor. And we're also going to look up protecting and deprotecting the para position. And then at the end, we'll go over Mascal's practice midterm 2 that he posted on his Canvas. Right. So first, let's go over polysubstitution and competition. So there could be multiple groups on the benzene ring, and there's going to be, let's say, most likely only one group that directs the electrophile, right? We know that strong EDGs will have the highest priority, right? That takes priority over weak EDG. So if you had two EDGs on the benzene ring, you would look at your strong EDG to direct the group, right? Now, let's look at the EWG. Which one do you guys think is going to be a stronger director, a strong EWG or a weak EWG? Right. Yeah, so a strong EWG will deactivate the ring because EWGs are deactivators, right? Weak EWGs do not deactivate the ring as much. So weak EWGs would take priority over strong EWGs. So that's the tricky thing. It's like the redox, reduction, oxidation thing back in Gen Chem. Because you know how in the EAS reactions, the benzene is the nucleophile. That benzene becomes a stronger nucleophile if there are EDGs on it, because the EDGs donate electrons into the benzene ring, making it a better nucleophile. If we have EWGs on it, that would make the benzene a weaker nucleophile because EWGs withdraw electrons, making it more positive. So that's why if you have EWGs on it, a weak EWG will take priority over a strong EWG. So that's the tricky concept there. Another way you can think about it is that a weak EWG does not deactivate the benzene ring as much as a strong EWG. A strong EWG deactivates the ring so much. That's why the weak EWG takes priority over the strong EWG. Okay, so there's going to be, let's say, 5 different scenarios. Let's say we have an activator versus a deactivator, right? Where A is going to stand for activator, and D is going to stand for deactivator. Okay. So let's say we have this benzene ring here, and we have an OH on that carbon and an NO2 on this carbon here. And let's put this through Br2, FeBr3. Okay, so we have multiple groups on the benzene ring. Which one of these groups will direct the bromine onto the benzene ring? Yeah, OH, right? Because we first have to determine what kind of groups we have on the benzene ring, right? Where OH is an EDG because it is partially negative with lone pairs of electrons on them. NO2 here is a strong EWG, right? That is because NO2 looks something like this, where we see that this nitrogen here of the NO2 has a full positive charge. It wants to gain electrons, making it a very strong EWG. And like we said earlier, EDGs always takes priority over EWGs. So the OH is going to take priority. And since this is priority, what positions are we interested in relative to that EDG? Ortho and para, right? Which are going to be either this position, that position, or this position here, right? This ortho position right there, there's too much steric hindrance because if we added a bromine here, like if you see 3 groups in a row, that's very bad. That's too much steric hindrance, right? So it could either go to this position or that position here, giving us these products here. bar, where that's the para product, and this is the ortho product, where we selectively go for this ortho position here, because this ortho position is too sterically hindered. Okay, let's do another example on this scenario, where let's say we have this benzene ring, and we have that group, and okay, the very first thing, identify what type of groups these are. What is this R group here? EDG, EWG, EDG, and it is a weak EDG. How about this nitrile? EWG, right? Because it is partial positive, and it is a strong EWG because it could do resonance, direct resonance with the benzene ring. Which takes priority, weak EDG or strong EWG? Yep, EDG. Even though this is weak, the EDGs always takes priority over EWG. So we are going to be considering these ortho and para positions relative to the EDG. We ignore this one because that's too sterically hindered. So if we do like nitration, let's say HNO3, H2SO4, the nitro group is going to be on these positions here. And O2, and the other product would be that right there. Okay. So that was the first scenario. Let's look at the uh-huh. Oh, right. So this ring here is like deactivated because it has a strong EWG. The reactions that do not work on deactivated rings are the Friedel-Crafts reactions, FC reactions, like Friedel-Crafts alkylation, Friedel-Crafts acylation. All the other EAS reactions like nitration, sulfonation, bromination, chlorination still work on deactivated rings. We cannot do Friedel-Crafts here. So the second scenario, yeah. Yes, they are both relatively major. Yeah. I will, you draw both products as the answer. But even though this is the ortho position to that EDG as well, we don't put the NO2 here because 3 groups in a row, very bad, very bad steric hindrance, too bulky. So the second scenario is going to be an activator versus another activator. So let's say we have this example here. It's going to be a little, and we try to sulfonate. We know the OH with the lone pair is an EDG, and the NH2 here, this is not NO2. NH2 is the polar opposite of NO2. NH2 is a EDG as well. We have 2 EDGs. Now, we saw in the ranking system, we want to choose the stronger EDG to direct the group. Which one of these groups is the stronger EDG? NH2, right? Because N is less electronegative, more willing to give up its electrons and donate electrons into the ring. Right. So this is the group that we are directing it. We're going to look at the ortho and para positions. But the para position relative to this NH2 is already blocked off by that alcohol. So we can't add a sulfonate group on the para position. We could only either put it here or here, but it's the same product. So we only get one product here. H, and this is going to be SO3H. There you go. Okay. The other scenario is very similar to scenario number 1. Activator versus deactivator, but they work together. And I'll show you what that means. Let's say we have this benzene ring here with this EDG alcohol on that carbon. And this EWG here, SO3H on that carbon right there. And we try to brominate it. Br2, FeBr3. Right? So we know EDGs. This is an EDG here. This is an EWG here. Relative to this EDG, the ortho and para positions are here and here. What kind of directing group is an EWG? What position does EWG directs the electrophile to? Yeah. Meta, right? Where we notice that meta to this EWG are these carbons here. And these are the only carbons that the electrophile could react with. So this right here are the only you EWG and like do this normally like how we did in the first scenario and just focus on the EDG. Because we know EDG always takes priority over EWG. So you could just ignore that. But we see here that they work together by having nothing here, like no directing group on those carbons. This is already blocked up, so we can add a group there. Right. So we are going to have a bromine there. Okay. Now, a tricky example is going to be the next scenario, deactivator versus deactivator. Okay. Let's say we have this and actually, yeah, this one here, this would not actually like be a problem because it doesn't matter which EWG we choose. If we chose this EWG here, the meta positions relative to this EWG are these carbons here, this carbon and this carbon, right? So if we look at this EWG, meta to this EWG is going to be either this carbon or this carbon. We see that the only position is going to be that carbon right there. So in this case, we didn't have to like choose one EWG. So let's change this up where we do have to choose one EWG. Let's say have something like this. This is an EWG. This is an EWG. Meta to this EWG are these positions here. Meta to this EWG are these positions here. Which EWG do we want to pick to direct the group? Like, let's say we want to do bromination. Which one does not deactivate the ring as much? Yeah, the carbonyl. Think of NO2 as like the strongest EWG. This carbonyl here is a weaker EWG. So we're going to use this carbonyl here as the directing group, which we're going to add the group's meta to that carbonyl. One more example with an exception. Let's say we have this benzene ring with this nitrile and then this bromine right here. And we try to nitrate it, HNO3 and H2SO4. Right. This halogen here is a weak EWG. This nitrile, think of it as a strong EWG. Which one would direct the NO2 group to the benzene ring? The bromine, right? And what positions relative to the bromine are we going to be interested in? Yeah, ortho and para. So this is the exception here. Even though this bromine is an EWG, right? It is ortho para director, not meta. director. So that's the exception. So the ortho and para positions are these positions here. Too much steric hindrance on that ortho position. So we get two different products here. Two. And the other product is going to be okay. Oh, right. So this nitrile here is an EWG because that nitrile, we know it has a triple bond with the nitrogen. And we know nitrogen is more electronegative than carbon, which makes that carbon partial positive. The very, very first atom directly attached to the whole system or benzene ring here is partially positive, making it an EWG, right? If this was NH2, then that would be an EDG. But this is CN, where C has a partial positive charge, making it an EWG. Okay. The last factor are going to be about steric effects. We already talked about this example here, where let's say we have this benzene ring with this aldehyde, and let's say this OCH3, and we try to chlorinate it, Cl2FeCl3. Okay. Which group will direct the chlorine here? OCH3, because that's a strong EDG, and ortho para to that. We already talked about this effect here. We can't add it to this position because that is too sterically hindered. We can only either attack this position or that position there, right? The other steric example is this right here. Okay, now we have two EDGs that have the same strength, right? Let's circle this EDG purple, ortho and para to that EDG, or these positions there. Let's say this is the blue EDG, ortho and para to that blue EDG, are these here, right? We cannot add, let's say we try to do Friedel-Crafts acylation. Right? They're both equally substituted, so it doesn't matter which one is going to direct the group. What does matter now is steric hindrance. We cannot add it to this carbon or this carbon because these carbons are already taken, right? So which one of these carbons is most likely going to attack the electrophile? Yeah, the purple one, because the purple one here has less steric hindrance. It is less like crowded, whereas the blue one has more steric hindrance because of third butyl group. Right? So it is going to attack either there or here. Which would give us this product. It doesn't matter which one because since this is symmetrical, it will give us the same exact product, but just rotated. That. And then for this one here, we get two different products. That and this. Okay, so the next thing we're going to talk about is converting ortho paradirectors to metadirectors or vice versa, converting metadirectors to ortho paradirectors. So let's start with a benzene ring with a carbonyl like this. What is the reagent that can reduce that carbonyl down into the alkyl group here? H2PDC, say H2PDC or zinc, mercury, HCl. Right. Do you guys know? Yeah. Oh, he didn't go over it? Okay. So let's ignore that. But if you see this on practices, right? Just think of that as H2PDC. Like if you do practice problems, when you see zinc HgHCl, think of it as H2PDC. Right? Do you guys know the reagent that would convert the alkyl group back into the carbonyl? How can we oxidize that alkyl group back into the carbonyl form? Oh, that's from NH2 to NO2. That's a different thing. That's still an oxidizing agent, but that's for NH2 to NO2. Right? We want to use a different oxidizing agent, which is going to be Jones in the form of chromium, O3, H2SO4, and water. Right? That would oxidize this alkyl group, specifically the benzylic position, the carbon directly attached to the benzene ring, to the carbonyl there. Right? Now, notice how this was an EWG, the carbonyl. That EWG we know is a metadirector. Once we reduced that carbonyl into the alkyl group, the R group, that became an EDG, an ortho paradirector. This is very important because for synthesis, right? When you want a group to be like ortho, para, or meta to each other, you have to use like these reactions if you want to go have a like meta position relative to this R group, but you want to have this first and then add a group meta to it, and then reduce the carbonyl to the alkyl group with whatever you added meta to that, right? And we'll look at examples with this after we go over these helper reactions for synthesis. Now, let's go over the NO2 to NH2. Okay, we have NO2. We could reduce that to NH2 using H2PDC. That becomes NH2. And like Eva said, we could go back into the NO2 by using MCPBA or a peroxy acid like RCO3H, but just use MCPBA, right? Where it does the exact same thing. It converted an orthopara, oh no, metadirector into an ortho paradirector, or vice versa. We could convert an ortho paradirector into a metadirector. We could go in between with these reactions here. Because NO2 is an EWG and H2 is an EDG. So now let's do a practice synthesis problem on this. This, and we try to make this here. Okay, try the synthesis problem for 3 to 5 minutes. And for this midterm, there is a very high chance that the synthesis problem is going to be on this chapter 16 with the benzene reactions. It's less likely for it to be an alkene kind of synthesis problem. It's more likely to be benzene. Oh, alkane back to ketone. Alcohol group. Oh, I think you're thinking about a different kind of reaction. I think you're thinking about Grignard, right? This is different reaction. This is oxidizing benzylic carbon to carbonyl using Jones. This is a new type of reaction. Right? And for this one, when you do Friedel-Crafts acylation, make sure to put a halogen there, like chlorine. Well, we're gonna substitute that. So for this synthesis from here, how did you guys approach this? So, what did you guys do first? Yeah, nitration first. Okay, yeah. So this is good. Let's see. What did you do afterwards? Alkylation or acylation? Alkylation. Did you use this reagent here? Let's say we have that. Did you use this reagent with AlCO3? Yeah. So this is going to not work because of two reasons. Is this a deactivated or activated ring? Deactivated ring. We cannot do any Friedel-Crafts reaction at all on deactivated rings, which is why we can't do nitration first, because this Friedel-Crafts will not work. Right. Another reason why it will not work is because this alkylation thing here, one of the limitations is rearrangement. When we kick out that leaving group, we know there's going to be an intermediate, carbocation intermediate like that, which can do a rearrangement step. In this case, we could do a methyl shift to get something like this, where now the carbocation would be right here, right? Let's say it like that was an EDG instead of an EWG, and it goes through, right? Let's say parallel to that is that we're gonna have two, where this carbon here is the dot carbon with the carbocation, which is that dot carbon right there, right? Because this dot carbon right here was the electrophile that got attacked by the benzene ring, which is attached to two methyl groups, 1, 2, 1, 2, and an ethyl group right there. If that was an EDG, this is what you would get instead of the CH2 terbutyl group, right? So we couldn't use Friedel-Crafts alkylation because of rearrangement, and we couldn't do nitration first because that deactivates the ring, which does not allow us to do Friedel-Crafts. This is deactivated. No Friedel-Crafts reactions. Okay. So what other thing can we do first? Yeah, we could do acylation first. Straight. Where the acyl group we want is going to be that acyl group. Imagine a carbonyl was right there at the benzylic carbon. That's the acyl group, right? Which is this group right here. Cl, AlCl3. That's the first step. Second step, acid workup. Add the acyl group right there. And we know this is an EWG and a meta direct there, which is perfect because we see that nitro group is meta to that group right there. So the next, yeah. Yeah, you could use BR as well. It doesn't matter. If you use BR, yeah, it doesn't matter, right? To be safe, if you use BR, I would also use like ALBR3 or FEBR3. Change the catalyst as well. So the next thing we could do is nitration to add the nitro group to the meta position relative to that EWG. Okay. And then this is the reaction we went over earlier. We want to cleave this whole carbonyl group off, and we can use the reducing agent, use like H2PDC. So the order of these benzene synthesis rounds matter a lot because yeah, there's different like directing groups. For Friedel-Crafts reactions, you have to watch out for deactivated rings. Yeah. 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 So for synthesis, I can only think of one example where you want to use alkylation over acylation, where let's say we have something like this, and we want to get into something like this right here, right? We know this is the R group here, and whenever you see new R groups on a benzene ring, think of your Friedel-Crafts reactions for benzenes. Back in 118A, when we added a new carbon-carbon bond or an R group, we thought of Grignard reagents. For benzenes, new carbon-carbon bonds, Friedel-Crafts reactions. We usually do Friedel-Crafts acylation, but let's try that. Let's see what happens if we try to do Friedel-Crafts acylation. Where we know this is the carbon right there. When we try to make that carbon have a carbonyl with a chlorine, there's something wrong here, right? Because that carbon right there has 5 bonds. 1, 2, 3, 4, 5. Breaks the octet rule. We cannot do that. Right? So this is where we prefer to do alkylation over acylation. So let me write in words. FC Friedel-Crafts alkylation over FC acylation. If you want to add a secondary carbon to the benzene. This is a secondary carbon. Wait, actually. Yeah. Secondary relative to the R groups. This is actually a tertiary carbon because it's bonded to 3 other carbons. Right. So let's make it more accurate and say if you want to add a tertiary carbon. Tertiary carbon to the benzene. This is a tertiary carbon here. And the only way we could do that is through the Friedel-Crafts alkylation reaction. Right. For the acylation here, this carbon here is a secondary carbon because it's only bonded to 2 other carbons. If you want a tertiary carbon, then you use alkylation. Okay, this is actually a good synthesis because this is going to segue to the next topic. So once we have that group there, we know that R group is an EDG ortho para direct there. But we see in the product, there is nothing in the para position. We only see something on the ortho position, right? So what do we have to do in the synthesis column? We can't just go to HNO3 right away because that would also react with the para position. Yeah, we have to sulfonate it. We have to block that group off. We have to use a protecting group like sulfonation. So SO3, H2SO4. And this sulfonate group, SO3H, will go para to this EDG here. It will not go ortho because SO3H is a very bulky group. Once that para position is blocked, we can now do the nitration reaction. Okay, now once we have this, we want to get rid of that SO3H group, deprotect it. And to deprotect it, we use strong acid and heat. H2SO4 and heat. You can use H3O plus as well, but I most commonly see H2SO4 and heat. That just gets rid of the sulfonate group there. And that gives us our desired product there with no para group. Yeah. Oh, the reagents to transform a ketone to regular alkane, H2PDC, but if you do like other practice problems, you could see zinc, mercury, HCl as well, right? That does the exact same thing. Same as for NO2 to NH2, NO2 to NH2, H2PDC, or zinc, mercury, HCl, okay. Reducing agents. So the reducing agent from here are the same, but the oxidizing agents are different. To oxidize the alkyl group back to the carbonyl, we use Jones. To oxidize the NH2 back to the NO2, we use MCPBA. Okay. So the next topic, ortho and para products. Okay. So let's say we have a benzene ring with an EDG. Let me make a OCH3, right? And then we try to brominate it, Br2 FeBr3. We know this EDG is ortho para director, where we're going to get two products, an ortho product and a para product. Right. There is a major and minor product here. Right. And we know that the major product is this one, the para one, because of less steric hindrance. The ortho one is the minor product because that's more steric hindrance. Right. Less steric hindrance. And then we already went over the next concept, which was the protecting the para position here. But let me write that more clearly. Because there is a way to selectively just go for the minor ortho product with no para product. And that's by protecting the para position. So this was 3. Ortho and para products. So like we said earlier, we could sulfonate that benzene ring using SO3, H2SO4. That would add an SO3H on the benzene ring. To get rid of that SO3H and go back to the benzene ring, we use strong acid, H2SO4, and heat. This is important in synthesis because if we only want the ortho product, we would have to block the para product. And this is how we block it. This blocks the para position. From the EDG. And then the example that we did with that is this example here. Right? Because we know that this was the EDG here, but in the final product, we did not want any group at the para position at all. So we had to protect it using sulfonation, which adds an SO3H group there. And then we added whatever electrophile we wanted ortho to that. It could be like nitration, bromination, chlorination. It cannot be Friedel-Crafts though, because this is an EWG right here. This EWG deactivates the ring, so we cannot do Friedel-Crafts in this next step. We did nitration, which still works as a nitro group to the ortho position, and then get rid of that whole SO3H group, deprotect it using strong acid and heat. There. Yeah. So that's all for the benzene stuff. Let's do some practice synthesis problems. I'll give you guys three to try. And then I think these are going to build up in difficulty. Actually, yeah, let me give you two. I want to include like a lot of reactions for these. Four more, or two more. The third one is going to be a little tricky. These four synthesis problems here. There are a lot of like considerations for these synthesis forms. Think about each group. What are they? EDG or EWG? Which one takes priority over the other? And if it's deactivated, you cannot do Friedel-Crafts reaction. And then think about if you need to protect the para position or not, or think about if you need to convert an ortho para director to a meta director or a meta director to an ortho para director. Mm-hmm. Mm-hmm. Yeah, it will do both. That's a good question. If you have an NO2 on the benzene ring and a carbonyl, like an aldehyde or ketone, on the benzene ring, and you H2PDC that, it will reduce both of them down. Yeah, one is just fine. Think of it as like when you react an alkyne with an H2PDC, yeah, to burn up alkane, it will overreact. Uh-huh. Yeah. 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 Oh, isopropyl, this one? Oh. Oh. Yeah, yeah. Nice catch, nice catch. Yeah, yeah. This would also convert the NO2 to NH2. So if we wanted this NO2 though, right? There's actually gonna be one more step. Right? Because let's say we still want the NO2 group there. This H2PDC here will reduce both the carbonyl and the NO2 into NH2. So let me make this smaller. Because this is this concept right here. where you know how if we have a NO2 or a carbonyl on the benzene ring and we use H2PDC, H2PDC will reduce the carbonyl down to the alkyl group, gets rid of the carbonyl overall. H2PDC will reduce the NO2 to NH2 here, right? So for this synthesis problem here, because I did H2PDC on this structure that has the carbonyl and the NO2, it will reduce both. The carbonyl would become an alkyl group like that, and then the NO2 would become NH2. Right. So there's one last step here. What can we do to convert the NH2 to NO2? Yeah, we can oxidize it. And this is a selective oxidizing agent because when we use MCPBA, which is the thing that will oxidize the NH2 to NO2, it will not affect the alkyl group. MCPBA does not oxidize it back to the carbonyl, right? So we are going to use MCPBA here. Let's say your final product, you wanted this instead, where you wanted the carbonyl back, but you wanted to keep this as an NH2. You would still oxidize it, but you do use a different kind of oxidizing agent, which is Jones, CrO3, H2SO4, H2O. So this is selective oxidation, right? It's selective because we get to select which one we want to oxidize, the NH2 or the alkyl group, right? In this blue product here, we wanted the alkyl group to oxidize to the carbonyl, but not the NH2. So we get to use Jones. But in this one here that we had originally, we wanted to get the NO2, but not the carbonyl. So we could do that by using MCPBA, which will oxidize that NH2 to NO2 there, right? For H2PDC here, this is not selective. It doesn't select for both, right? It will it doesn't care. It's overreactive. It will react with both of these here. It will reduce both of them into its reduced form. Yeah, nice catch, nice catch. Does anyone want to come up and try the first one on the iPad here? It's okay if you guys make mistakes because other people might make the same mistake too, and then it's a learning process. Yeah, you can try. Nice. Ah. Where for this synthesis problem here, this is the thought process of what I think about. I think about what's similar in between the reactant and product. We have that benzene ring with the OCH3, which is that same exact OCH3 right there. The new thing that is added is this bromine here, right? And then I look at the relationship between those two groups. The relationship between that OCH3 and Br are ortho. They are ortho to each other, right? So I know that OCH3 is an EDG, which is an ortho para director. So I can't go from here to here in one step by using like Br2 FeBr3 right away, because the para position can attack the Br instead of the ortho, but we don't want that there. We don't want anything on the para position. So we have to use a blocking group. We have to protect the para position by using sulfonation first to block off that para position. And once that's blocked off, then we can do the bromination to add bromine to the ortho position, and then get rid of that SO3H group by deprotecting it using H2SO4 and E. Any questions on this synthesis problem? Okay. Does anyone want to come up and try the second one? Yeah. Oh, eraser. Yeah, eraser is, or you could go backwards, undo right there. Yeah. The first step, protect the para position, because we see that this is an EDG, which is an ortho para director, and we see that this new group that we added onto the benzene ring is ortho to that EDG. We want nothing on that para position, right? So we have to first protect it using sulfonation. And then this new group here has a nitrogen on the benzene ring. There's only one EAS reaction that we learned about in benzenes that adds a nitrogen to the to the benzene, which is nitration, right? But it doesn't add an NH2 group. It adds yeah, it adds an NO2 group, right, with the para, like the sulfonation group still there. And from here, the order does not matter. You could either Now we want to convert the NO2 to the NH2 by reducing it using H2PDC. Nice. Yeah, no, that's good. That's good. Nice. Where from this point here, the order of these reactions do not matter. You could use H2PDC first and reduce the NO2 to NH2 first with the SO3H2 there, and then deprotect it. In this case, it doesn't matter because the H2PDC will like only reduce the NO2. The H2SO4 will only deprotect the sulfonation group, right? Any questions on this synthesis problem? Okay. Has anyone been able to figure this one out with the weird ring on the benzene ring? Okay, so for this one, the very first thing, look at all the groups and figure out if there are EDGs and EWGs. A tip that I like to do to determine if a group is an EDG or EWG is look at the very first atom attached to the benzene ring and see if it is partial positive or partial negative. If it is partial positive, then it's an EWG. If it's in partial negative, then it's an EDG. Right? We know the bromine here or any halogen is a weak EWG. Right? Now let's look at these atoms here. I am focused on those atoms because those are the first atoms attached to the benzene ring. Ignore the other atoms. The other atoms there are not directly attached to the benzene ring, right? This right here, think of that as an R group because there's no carbonyl there. So since that's an R group, this is a weak EDG. Right? This carbon here is double bonded to a carbon to an oxygen and is partial positive, making this this is a moderate EWG. Okay. Once we figured out all the groups, the EDGs, EWGs, now we select the one that has the highest priority. We said earlier, EDGs always takes priority over EWG. So this right here is our directing group. So we know EDGs are ortho para director. So let's find those ortho and para positions relative to this EDG here, which are these ortho and para positions here, right? Now, this ortho position here is already blocked off. We can't add anything else there. This ortho position here is too sterically hindered. We can't add anything there as well. Too much steric hindrance. The only position where we could add groups is this carbon now, which is perfect because we see our new group here has that new group, which has a nitrogen directly attached to the benzene ring. And the reaction that adds nitrogen to benzene ring is nitration. HNO3, H2SO4. But it doesn't add NH2, it adds NO2. And then from here, we can go straight to here by reducing it using H2PDC, right? Which will reduce both the NO2 and the carbonyl into that form right there. This could get harder if, let's say, your carbonyl was still there, right? Like let's say instead of this product, we wanted this product instead, right? How would this change here? What would we do? Selectively oxidize it. We still do the same first step, H2PDC, which will give us the same thing here. And then from here, we want to selectively oxidize. Oh, wait. This is going to be a problem because there's two benzylic carbons. Okay, let's put that there. Okay. Where to get from here to here, we use Jones, CO3, H2SO4, H2O, which will oxidize both these benzylic carbons into these carbonyls here. Okay. So if you wanted this product instead, then you know that this reaction was used, the Jones reaction. Yeah. Wait. We have three separate groups here: the bromine, this carbon, and that carbon right there. This bromine is a weak EWG. This carbon here is an R group because it's not double bonded to anything. This carbon here is a carbonyl that is partial positive because it is attached to an oxygen, right? And because it is partial positive, it is EWG. EWG. So we want to choose the group that activates the benzene ring, that makes the benzene ring a stronger nucleophile and gives it more electrons, which is always the EDG. We always choose EDG over EWGs because they activate the benzene ring. They make it a stronger nucleophile. EWGs deactivate the benzene ring. They make it a weaker nucleophile. So the directing group is always the EDG in this case. But let's say the EDG wasn't there. What group would direct the benzene ring? Oh yeah, so this is the tricky one here. Because you know how EWGs deactivate the ring? We want the group that does not deactivate the ring as much, right? Which is going to be the weak EWG. So that's tricky, right? Because the priority is like strongest EDG is always highest priority, weak EDG, and then weak EWG, and then strong EWG, right? Another way you can think about it is this right here. Instead of that, like that's kind of confusing, is this. Activate their power, always highest priority over deactivator power, right? That's another way to think about it. Instead of thinking about the strong EDG, weak EWG, or weak strong EWG like that, right? This is always the case. You always choose the strongest activator over the deactivator. Right? We know these are both deactivators because they are both EWGs. But this is a stronger deactivator because this is a stronger EWG. But that's bad. We don't want a deactivator. We want the one that does not deactivate the ring as much, which is this one here. So that's probably the better way to think about it. Okay. So that's it for the benzene like synthesis practice problems. Yeah. Oh, wait. It forms two carbonyls because the Jones reagent here selectively oxidizes benzylic carbons, right? And we have two benzylic carbons here, 1 and 2. Yeah. It does not make this carbon here a carbonyl because that is not benzylic. Yeah. Oh yeah, I forgot. We have one more. Does anyone want to come up and try this one? Yeah, you can try. Right. So for this one, you notice how you starred these carbons because there are ortho to the chlorine here. there's also para as well. So it could also add the nitro group para to that, right? But we don't want that at all, right?
So do we do the roadblock thing in this case?
Yeah, so
Or
we can.
would it be too sterically hindered?
Oh, I see what you're trying to do. Oh yeah, actually your way works as well. Your way works as well. Yeah, I think. Yeah, this way works as well. Nice. Yeah, this was a different route than I intended it, but I just realized this works as well. Nice. Yeah. Okay, so for this one here, we did Friedel-Crafts acylation with that acyl group, and make sure to include the metal catalyst AlCO3 as well, which adds this acyl group on the benzene ring, which is an EWG meta director, right? Which will add the chlorine meta to that EWG. Once we did that, now we have two different groups. We have a weak EWG versus a moderate EWG. Now this is in my opinion, the trickiest two groups to compare, like the two EWGs, right? Because a lot of people would always choose the stronger EWG because they think stronger is like better, but not the case for EWG. Think of it as like which one is less deactivating. The one that's less deactivating is this weak EWG chlorine here. So this is the directing group, not this here, right? And this is the exception. Even though this is an EWG, this is a halogen. It's not a meta director. It is an ortho para director because it is a halogen, right? Which the ortho and para positions are going to be these carbons are ortho to that EWG, and that carbon is para to that EWG. Right? We cannot add any group here because that is too sterically hindered. 3 in a row, very bad. Right? We can do nitration, which would add a NO2 group to that ortho position, which is probably major because chlorine is smaller than this big group right here. And once we have this group, what will H2PDC do to this whole structure here? Will it oxidize one or both groups here? Both groups, right? Which will get to the NH2 and then get rid of the carbonyl, which is what we want. Get rid of that carbonyl in the final product. But we wanted to keep our NO2 group, right? Because after we have reduced both, we get this. Oh no carbonyl. Cl, right? But we did not want this NH2. We wanted the NO2. So we could selectively oxidize this NH2 by using MCPBA. We don't use Jones because Jones would get back to your carbonyl. Yeah. The way that I thought about it was this right here, which let's see if it works. But that's also acceptable. Yeah, for synthesis, there's multiple correct routes that could work. For this one, I did the same first step. Friedel-Crafts acylation. Step. Oh, and also for acylation, they require a second step of acid workup. So first step, second step, acid workup. Which will add the acyl group to this carbon. And then chlorination to add the chlorine meta to that EWG. And then from here, I reduced first using H2PDC to reduce that into the R group that we want, which is an EDG ortho para director. which is ortho para to that, and we could go from here to here using nitration. Right, which this is probably the major one because NO2 is less sterically hindered here. It can't go here because that's too sterically hindered. It could go here, but that's probably minor to this one here. Right, so this one could also work. Yeah. From which point here? Oh, the green one here. Right, we don't want to block it because we want our nitration group there. Right, if we block it, think of the blocking group as the SO3H group, right? We don't want an SO3H group there. We want an NO2 group there. Or like block it with SO3H. If your product was this instead, like you wanted, let's say, that's a good question because if you wanted this product instead, then you would have to block this para position because we don't want anything there. Then you would do the SO3H, nitration, and then deprotect that para position. But if we wanted this right here, which this carbon is para to that group, we don't have to block it because we want that open for the group to attach there. So if this was your product, then you require like two more steps, protecting the para position and deprotecting the para position. So let me make that note. More, and then nitration, and then deprotection. Where this is the protecting step. Protect para. This is deprotecting step. 2 extra steps. And this protecting group of stuff, right? This is going to be a common theme for the final unit, like after midterm 2 with the carbonyls. Deprotect. We still have the nitration step there. Yeah. Yeah. So for the deprotecting step, let me write this out here. We know that for this product here, you know how this is the EDG right there, which is an ortho para director. In the final products here, we do not want any group on that para position there, right? So the reaction that blocks the para position is sulfonation, right? So once we do sulfonation, we are going to have that group on that para position, which blocks the para position because when we do nitration now, right, it cannot go to that carbon anymore. It's already blocked off. It could go here, but not here because this is too sterically hindered. It can only go here now. Once we do nitration, we want to get rid of this SO3H. And to get rid of this SO3H, we introduce strong acid and heat, which gets rid of that whole thing, the SO3H. Okay, that's all for benzene synthesis. Do you guys have any questions on this unit? So have you guys tried Pascal's practice midterm 2 yet? Not yet. Okay. Let's see. How can we do this? Vocab, mechanism, predicted product. Oh, try this. Try Pascal's Yeah, HOMO-LUMO orbital. Yeah, let's go over that after this. Yeah. Wait, we did this yesterday already. Yeah, so let's just go to the HOMO-LUMO stuff right away. HOMO-LUMO. Okay. Okay. So for Diels-Alder, we have a diene reacting with a dienophile. That under heat will give us a cyclohexene adduct. it's just a cyclohexene with other groups attached to it, like random stuff, random EDGs, EWGs. But we always have a cyclohexene. Our diene looks like this, where it has to be in the S-cis configuration. Our dienophile is one alkene like that. We put that under heat, right? These are going to be the arrows. We are going to create this cyclohexene adduct here. I like to number these atoms 1, 2, 3, 4, 5, 6 to keep track of every single group and make sure the groups are attached to the right carbons. So that's the general mechanism of that, where behind the scenes, the HOMO of the diene interacts or reacts with the LUMO of the dienophile. Okay. So let's draw the molecular orbitals of both the diene and dienophile. We know our diene could be in this S-trans configuration like that. This is in the conjugated system here, right? How many electrons in this system can do resonance with each other? Yeah, 4 electrons. 2 from this bond, 2 from that bond right there. They could do resonance with each other, where the 4 electrons here will make up the 4 molecular orbitals of the system, because the number of electrons that are resonating with each other is equal to the number of molecular orbitals. So this 1,3-butadiene here, or this structure, has 4 molecular orbitals. I'm going to draw in this graph here with the energy, where the energy is highest up here, lowest down here. Okay. Do you guys know the hybridization of these atoms here, of the conjugated system? sp, sp2, sp3. Yeah, sp2, right. That means that these atoms here will have p orbitals on them, like that. Right. So that's 1 molecular orbital, 2 molecular orbital, 3, and 4. And we have 4 because we have 4 electrons. The lowest energy one, is that the most stable molecular orbital or the least stable molecular orbital? The one that has the least energy. Most stable, right? And the most stable, think of it as the one that has the most amount of resonance conjugation. So all of these p orbitals here are going to overlap with each other, right? So the shaded thing represents electrons. Those electrons are going to be overlapped, flowing with each other, like that. As we increase in energy of the molecular orbitals, we're going to introduce a node. So there's one node there, which separates the flow, right? So there's going to be a flow between these orbitals, but that node separates these 2 orbitals here. So we get that and that. As we increase the energy again, we increase it by 1 node. So now we have 2 nodes here, which separates the charges like that. There's no node there, so that's the overlapping, where we only get 1 overlap, like that. Increase the energy again, the highest energy one will separate all of those p orbitals. Right? There's no overlap between these orbitals here. Up, down, down. Like that, right? Where there are no overlap of electrons. Another way to think about this or visualize this is to draw in your butane and draw electrons flowing all throughout the molecule, which represents this molecular orbital, where the electrons are overlapping with each other like that. This one here is what we're used to seeing the most, where the electrons here are flowing between these 2 carbons and these 2 carbons here, which represents these 2 and those 2. We know that this can do resonance by pushing that double bond there and giving that carbon a negative charge. When we get that, we also have a positive charge on the other end, this end here, because this carbon lost the bond. And these are resonance structures because the charges are conserved. This is neutral. This is also neutral because the charges cancel out. Right? Which represents this molecular orbital because there's only electron flow between the middle carbons, which is those middle carbons right there. We could do resonance again by pushing this lone pair onto that carbon. We push it onto this carbon because we want the electrons closer to the positive charge. We don't want it closer to the negative charge, which will give us this resonance structure here. Right? Where this represents this molecular orbital where there are no double bonds in between the atoms. The atoms have separate charges. This is the least stable resonance structure, making it have the highest energy. Most stable, lowest energy. Right? Now, each molecular orbital is able to hold 2 electrons. We said earlier we had 4 electrons. So that's going to be 1, 2. Each orbital can hold 2 electrons. So that's 1, 2, 3, 4, like that. Right? I'm going to separate these molecular orbitals into 2 categories. This category here is the occupied category. They are occupied by electrons. This category here is the unoccupied category. They are unoccupied by electrons, no electrons in them. Yeah. Yeah, we want to fill in the electrons at the most stable configuration, most stable orbital first, which is the one with the least energy. And then once we fill that up, we move on to the next highest energy. Oh yeah, like I don't, this molecular orbital stuff, like I'm not too familiar with, but yeah. That's what I know. Like it goes for the lowest one first, and then it goes on to the next one. Yeah. Great. Once we have that, let's now define HOMO and LUMO. HOMO is highest occupied molecular orbital, MO. LUMO is lowest unoccupied molecular orbital, MO. So based on those definitions, let's say this is 1, 2, 3, 4. Which one of these 4 orbitals is the HOMO and which one is the LUMO? Yeah, wait, 2, wait, which one's the HOMO? Which one? Yeah, 3 is the HOMO, right? And which one's the LUMO? 2, right, 2. Right. So a tricky question is like they might ask you which one has higher energy, HOMO or LUMO? LUMO, right? And that's tricky because some people might choose HOMO because of the highest and they think of higher energy from highest, but that's not the case because we see that the HOMO here is lower energy than the LUMO. Yeah. 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 Occupied meaning that the orbitals here are occupied with electrons or they have electrons. Unoccupied meaning that they do not have electrons. Oh yeah, they do have electrons in the atomic orbitals. Like the atomic orbitals, like on the actual OChem thing that I'm like familiar with. But this molecular orbital stuff, like it's something I don't know. I'm just too sure why. Like I'm not too familiar with this stuff right here, right? Because where we draw these 4 molecular orbitals here, we see that these 2 molecular orbitals are filled with electrons, but those 2 molecular orbitals there are not filled with electrons. There are electrons on all of them, but those are the atomic orbitals. These are the molecular orbitals here. Yeah, where these are unoccupied because those molecular orbitals have no electrons on them. Yeah. Let's see. Okay. So let's answer the vocab questions related to that. Say, let's do these 2. So part D is asking for the LUMO of 1,3-butadiene electrons. Like how many electrons are in that molecular orbital? None, 0, right? Because the LUMO is this LUMO molecular orbital here. 0 electrons, no electrons on them. If they were asking for the HOMO, then the answer would be 2 electrons. When I first saw this, I thought it was 4 as well, because I saw like 4 electrons all throughout, like 4, 2, 4, 2, 4. But these are atomic orbitals. These are molecular orbitals, which are different than atomic orbitals. And LUMO and HOMO is a molecular orbital. It's MO. Yeah. The HOMO always has highest occupied molecular orbital. Not always the case. For 1,3-butadiene, yes, but not the other cases with like this example here. Say is weird. This cyclobutadiene, we could draw the Frost circle by rotating this whole group like that, where we have to have a vertex at the very bottom like that. Once we have that vertex at the very bottom, we make a circle around that diagram and draw the molecular orbitals like this, right? We know there are 4 electrons resonating with each other because 2, 4 electrons. That means 4 molecular orbitals. 1, 2, 3, 4. Okay. So there's gonna be 4 electrons here, where 2 is gonna go here, and then this cyclobutadiene here will exist as a biradical. Biradical, where we have radical on each of these orbitals here. One on this orbital and another one on that orbital, right? Where we can't add any more electrons because we already used up all 4 electrons. 1, 2, 3, 4. Right? So the HOMO highest occupied molecular orbital. Like these are the highest occupied molecular orbitals because they're occupied with the electrons, but they don't always have like 2 electrons on each. So that's an example where the HOMO of this one does not have 2 electrons. Okay, but we don't have to worry about that for Diels-Alder. That's more for conjugated systems. Okay. Now let's do this question here. Part E. Right, the first option. HOMO of the diene and LUMO of the dienophile react with each other. They interact with each other. And I'm going to show you guys why now. Let's draw in the molecular orbitals of a dienophile. Right? How many molecular orbitals would this dienophile have? Yeah, 2, because they have 2 electrons, meaning we have 2 molecular orbitals. Right? So let's draw the energy graph. Energy. We know that these carbons have p orbitals like that. P orbitals. Increase energy, increase the node. No overlap. This lowest energy one has overlap. Okay. Where this structure represents that molecular orbital, this structure represents this molecular orbital. Oh yeah, molecular orbital, 2 electrons, 2 electrons. This is the HOMO. This is the LUMO. Right. Now let's relate this back to Diels-Alder, or 4 + 2 cycloaddition. So I'm going to draw the diene like this on top and a dienophile on the bottom. We know that there are p orbitals on all of these carbons like that. We are going to draw in the HOMO of the diene and the LUMO of the dienophile. So let's go back and see what the HOMO of the diene looks like. This is the HOMO of the diene, which has one node in the middle between the diene. So let's put that one node right there. For the LUMO of the dienophile, we also have one node in the middle. So let's put that one node right there. And then I'm going to draw in the shaded electrons. Like that, right? Where notice how the bottom lobe of this p orbital overlaps with that top lobe of that p orbital right there, right? This interaction here is the interaction between the HOMO and LUMO that allows the Diels-Alder reaction to go through, right? This bottom lobe of this p orbital overlaps with that top lobe of that p orbital because there are no electrons there. They match up like that, which is why the HOMO of the diene, which is this one, interacts with the LUMO of the dienophile because they are able to overlap and match like that. Right. Okay. I think that's it for the HOMO-LUMO like stuff. It's more theoretical stuff, not predictive product, but like what happens behind the scenes. Yeah. Okay. Do you guys want to try the predictive product questions now, or the mechanism question here, this one, or any other topics you guys want to go over? Yeah. Oh, conrotatory, disrotatory, electrocyclic reactions. Yeah. So for those electrocyclic reactions, there's going to be this graph right here where you have different pairs of electrons reacting. You could either have an even pair or an odd pair of electrons reacting. And I'll give practice problems after this graph. And you could react this under either heat or light. And then to memorize that, I think of CD, DC. C meaning conrotatory, D meaning disrotatory. Wait, is this right? I'll make sure. Yeah, conrotatory, disrotatory. Yeah, that's right. Where conrotatory will mean that you will rotate your groups in the same direction. So either clockwise or counterclockwise. Disrotatory, you rotate your groups opposite direction. Disrotatory. Opposite direction. And there are two types of electrocyclic reactions that you could do, either ring closing or ring opening. And this is the thumb rule here to help you predict the stereochemistry of these reactions. This follows the Woodward-Hoffman rules. Woodward-Hoffman. And I think that showed up on one of the vocab questions, which is this one here, part F. The stereochemical outcomes of electrocyclic reactions was first described by Woodward and Hoffman. Right. Zaitsev is for like elimination reactions like E2, E1. Markovnikov is like the more subside. Anti-mark is the less subside. Diels-Alder, that's something else. That's Diels-Alder or cycloaddition reaction, not electrocyclic. Joule and Smith. I don't know who Smith is. Joule, I'm guessing he found energy. I don't know. He made the unit for energy. Yeah. Woodward and Hoffman made the electrocyclic reactions. So for the thumb rule, right? You're gonna start your thumbs a certain way and then end your thumbs a certain way. For ring closing, you're gonna start your thumbs either left or right, and then you're gonna end your thumbs up or down. For ring opening, you start your thumbs up or down and end your thumbs left or right. It's easy to see and understand this with examples. So let's look at some examples now. Let's say we have something like this. And let's do two examples, ring closing and ring opening, where we are going to have, let's say, that and that. And let's do both conditions, heat and light. Okay, let's look at this one first. So let's draw in the arrows of the electrocyclic reaction. Right. What would this reaction be? Ring closing or ring opening? Closing, right? Because we are going to close a ring or form a ring with these three arrows here, right? Look at your number of arrows and figure out if it's even or odd. Since this is 3, this is an odd pair of electrons. So we look at the odd row here, and then we see that under heat it is this rotatory, and under light it is conrotatory. Okay, so now let's draw in the template product, which looks like this here. We still have the CH3s on these carbons here, but they came from an sp2 carbon, which was flat and planar, to an sp3 carbon that is now not flat and planar. So they're either going to be wedge or dash. And to tell that, we do the thumb rule, conrotatory, disrotatory, right? So let's look at this group here. Is this group going up or down? This first bond here. Up. How about this group here? Down, right? So they are trans to each other. Don't start your thumbs up or down like that, right? Because even though this is going up, this is going down, don't start your thumbs up like up and down. We're ring closing, so we're gonna start our thumbs left and right, right? One thumb's gonna go left, one thumb's gonna go right. Let's look at the heat conditions. So that's this rotatory. Let's say my left thumb rotates clockwise like that. What direction does my right thumb have to rotate? Counterclockwise, which is gonna go here, the same side. Wait, going this way is clockwise, right? Like this rotatory, a lot of people think that this rotatory is opposite, right? So they automatically always want to make this opposite to each other, but that's not always the case. This rotatory means that the rotation direction is different, where since I did this clockwise, I have to do this counterclockwise, which they end up cis to each other, the same side. Right? Does that make sense? Okay, right. Because it does have to be clockwise on this side. Let's say this was counterclockwise, right? If I made this counterclockwise, this has to go clockwise, which is still cis to each other. So for this rotatory, the methyl groups here have to be cis, either both wedge or both dash, right? This rotatory does not always mean that the groups are trans to each other. This rotatory means the direction they rotate is opposite. Okay, now let's look at the conrotatory example. Let's say my left thumb rotates clockwise. This will also have to rotate clockwise, like that. Yeah, the most difficult part for me in these types of reactions is figuring out what direction is clockwise and counterclockwise. Like I always have to think about what's going clockwise, right? Like clockwise is this way, For this thumb, I want counter-rotatory, so I will also want to rotate clockwise, which is this way. So I see that they're trans, so I have to make them trans to each other. And here's another common thing that people mess up on. Let's say I have this right here. So we know that the arrows are going to be like this. Okay, so this is when we determine if they are trans or cis to each other. Always look at the very first bond coming out of the system, which is that bond right there, right? As some people, they look at this bond right here and that bond right there. But these bonds are not the first bond coming out of the system, right? So don't look at those bonds. Look at these bonds here, the ones coming out of the system, right? Everything else is a distraction. So we know that this is the same as like the last example, where this is con. So when we close the ring, we get the same stereochemistry, but different group. That. Okay. Let's do one more ring closing example and then move on to ring opening. Let's say we have this, that, then this. Okay. Try these. Here. Let me put the table down. Yeah. Oh. Oh, right. So this is ring opening, right? Because we're opening up the ring. Wait, let's draw the arrows of the ring opening. What arrows happened for this ring opening reaction? How many arrows even pair? So that sneaky thing here is that single bond right there. Because usually when we think about the shifts, we think about double bonds. But for ring opening, there is that single bond that counts as well. Yeah. Yeah. Oh, sterically hindered. I've seen some examples where the reaction does go through. So like you know how this is the in group because that's going in the bucket. They have to be trans to the EWG. So I've seen some examples where they put like that, but for Maria Jones, she puts no reaction because she says that's too much steric interest. They can't react. But Mescal didn't go over. Oh, this is in office hours. Oh, oh. Okay, that's good. Thanks for letting me know that Mescal does that too. So if there's two in groups like that, right, where there's too much steric hindrance, you know how the diene, the HOMO of it, overlaps with the dienophile of the LUMO of the dienophile. These groups here will block the orbitals from interacting with each other. Too much steric hindrance there. Down, I know. That's the examples I've seen before, but some people say there's no reaction because there's too much steric hindrance. Like it stops it from happening. So Pascal said that too. So like I would go with his word. Oh yeah, Eva, you know how that Diels-Alder practice problem you did with Mary Jones with the two in groups going in and with the no reaction thing, steric hindrance, Pascal said that there's also no reaction for that as well. So when you see that in the exam, just put no reaction. Yeah, yeah. I'll go over that too here before today. So for this one here, right? Let's draw the arrows of this ring closing, which are these two arrows here, right? We know that's an even pair. Even pair under light is disrotatory, under heat is conrotatory. Right? We know this group here is going up, this group here is also going up. So they're going on the same side, cis. Let's look at the light, disrotatory. If I rotate this thumb clockwise, the other thumb has to go counterclockwise. This way. Wait. Yeah, this way. Or is that what you guys got too? Like they're trans to each other for this one? Because we know that these two groups are going in the same direction, up. And for this rotatory, clockwise, this has to go counterclockwise, which is this way. Yeah. So now they're trans. Yeah. So that's how I do that one. And then for the conrotatory one, they're gonna go in the same direction. This is easier to do because like they're both same direction, both clockwise, yeah, or both counterclockwise. Okay, now let's do some ring opening examples. Well, in my opinion, ring opening is a little bit trickier than ring closing. Let's say we have heat and light. Okay, this is trickier because before we could have just counted the number of double bonds that are moving to count the pairs of electrons, which are two pairs here for ring closing. But for ring opening here, this single bond right here counts as a pair of electrons that's also reacting, right? Because that single bond is going to break and make a double bond there. So instead of thinking about the double bonds or single bonds, just think about how many arrows you drew for the reaction. If it's an even pair of arrows, then you go for the even pair, right? Some people think this is an only one odd pair because they only see one double bond. But this is a sneaky single bond here that also reacts, that also moves, right? So don't think about double bonds, think about your arrows that you drew. There are two arrows, so it's an even pair, right? So since it's an even pair, under heat, that's con, under light, that's this. Okay. So let's draw that template out like this. And we're gonna get two different ones. This is why this is trickier. Say we have that. Okay. The Turk butyl is gonna go up because it's wedge. The methyl is gonna go down because it's dash. For conrotatory, let's say I move this up group clockwise, right? Then this group would also have to go clockwise. Yeah. I see that they're facing towards each other. So this is one of the products. Now, let's say instead of rotating clockwise, I rotate this up group counterclockwise. Conrotatory, this would also have to rotate counterclockwise, where now they're facing away from each other, which will be this. Here, we can clearly see that this is major and this is minor. So ring opening, there's actually like different products, and you get major and minor because of less steric hindrance here. Yeah. Yeah. So let's start with your thumbs. How you start with your thumbs? So let's do up and down, right? For conrotatory, how do you want to rotate this group here? Clockwise, right? So that means this has to go also clockwise, which is that way, right? Now they're facing together. If you try the other way, counterclockwise, this would also have to go counterclockwise. that way, away from each other. Uh-huh. Yeah. Uh-huh. Nice. Uh-huh. So for this rotatory, let's say this is, oh my gosh, clockwise. This would have to go not clockwise, counterclockwise, like that, right? Which gives us this right here. Okay. Now instead of clockwise, we could go counterclockwise. This would also have to go. Oh no, this is opposite, so this would have to go clockwise. So this direction. So we could get that, or yeah, where this is the major one. This is the minor one. And this is because our bulkiest group, the tert butyl, here is facing away from the system. Less steric hindrance here, more steric hindrance here. Yeah. Uh-huh. Oh, for ring closing here, you could draw two, or you could say plus enantiomer. Yeah, you can't do it for the ring opening as well because there are no chiral centers here. So there are no enantiomers here. These are just you can think of it as diastereomers, like a cis and trans. Like this is a cis double bond, this is a trans double bond, or geometric isomers. Yeah. For the exam though, if you put all of them and like label them major, minor, I think you'll get it. But yeah, that's what I would do. I would put both of them and label major and label minor. Draw the major one first though. Okay. So that's why the ring opening is trickier because it has major, minors. And also this sneaky single bond here that's also resonating. No, not resonating, reacting. Right. Okay. So let's end off with this Diels-Alder problem here. Actually, let me just give you S2 because this one is, yeah, this one's gonna be quick. that first one that I gave you. Let me give you guys. Try these two, Diels-Alder. Oh, wait. For the Diene, put the methyl group down here instead. Okay, for the second problem. Right. So for the first one here, we see that these are in groups because they are facing inward toward the pocket, where these here will actually block the interaction between the HOMO and LUMO of the Diels-Alder reaction, right? So because of steric hindrance, no reaction for this one. This right here is different than this, because if you had something like this instead, there would actually be reaction. Don't confuse that with this. This would actually give you this product here. Because this is fixed diene, which makes the reaction rate way faster. This diene right here is not fixed. It's not in a ring, but that introduces steric hindrance, which is very bad. It blocks the diene and dienophile from reacting with each other. So that one is no reaction, right? So this here is not fixed. It has steric hindrance. The bottom one here is fixed. Increase reaction rate. Okay. Okay, for this one, charges do not align. We would have to flip it to make the charges align. And then we could react to make this product here. The out group is cis to the EWG. This methyl group here is trans to that EWG, so we have to make that trans as well. Right. Do you guys know how I got these partial charges there on those carbons? Right. I got these from the resonance. If you see that this EDG here donates electrons like that, push that double bond there, this double bond will give that carbon a set of electrons with a negative charge, which is why there's a partial negative charge here. This carbon is partial positive charge because this withdrawn group withdraws electrons from that dienophile, giving that carbon there a full positive charge right there, right? We want the charges to align, but they don't right now, so we have to flip it upside down to make them align and then go with the reaction. And then we use the endo rule to see the cis and trans stuff. This is an out group because we see that that group is outside of the pocket. Out group cis to EWG. This methyl group is trans to the EWG, so that stays trans to the EWG for the dienophile. Right, nice. Yeah. The out group cis to the EWG would be endo, right? The out group trans to the EWG is exo. Yeah. And another thing for endo is that the in group is trans to the EWG, because if let's say you had an in group like a methyl group down there, that would be trans to the EWG, right? This is an in group because it's going inside the pocket. In group has to be trans to the EWG for the endo. Out group has to be cis to the EWG for the endo. Okay. Yay. We finished.